So we've talked about functions in general. We've seen some specific kinds of functions. We've played around with functions as far as graphing some stuff too. So let's talk a little bit more in general about functions, specifically operations on functions. And of course, the first collection would be the obvious kind. If functions are just kind of fancy versions of stuff that we're already much more used to, like numbers, aren't there basic things that we can do with functions? Since function values are y values are just numbers, can't we just do some of those same sorts of basic things like add, subtract, multiply, and divide? Well, yeah, you bet we can. As long as we don't try to divide by 0. So, yeah, no big whoop. So, just to really, hammer away at the idea, let's say that we've got a function f of x equals x squared minus 3x plus 2, and we've got a second function g of x equals negative 2x minus 5. Let's find f plus g, that's a shorthand way of referring to the addition. F minus g, a shorthand way of referring to the subtraction. Fg, shorthand way of referring to the multiplication. And f over g, a shorthand way of referring to the division. Now, we would really want to say, to be super duper clear, parentheses f plus g of x, so still using that function notation, but again, the idea behind these basic operations is that these are just really straightforward. So if that said f plus g, all right, take the f function, take the g function, add those suckers together. So x squared minus 3x plus 2 plus the negative 2x minus 5. Okay, well, we know that we have some basic expectations about simplifying things, and combining like terms is in that basic list of expectations. So if we combine our like terms, we get the x squared minus 5x minus 3. Moving on to the subtraction, again, parentheses f minus g of x. For that official function notation, we're talking about doing f of x minus g of x. As usual with subtraction, we want to be careful. We want to make sure that we're going to distribute that subtraction, push that negative through, however you might like to say it in your own words. So we've got our f function, x squared minus 3x plus 2, minus, and our g function gets put inside parentheses because we know that we've got to be careful about subtracting. So parentheses, negative 2x minus 5. Combine like terms after you've simplified your subtraction business. Get your final answer, x squared minus x plus 7. Fg, in parentheses, of x would refer to, again, multiplying. So f of x times g of x. And in that particular case, we can just go ahead and take the f of x function, slap it inside some parentheses, take our g of x function, slap it inside parentheses, and hopefully we're not expected to do anything more with that. We've accomplished the multiplication, but watch out for any specific instructions where they tell you you do need to actually go through the time and trouble of multiplying everything out. If you have that in your instructions, make sure that you've tipped to that. F over g of x means f of x over g of x. Put your f of x function on top of a fraction bar, put your g of x function on the bottom of a fraction bar, and there it is. Again, that's it. So for many of our examples of multiplying and dividing, those are going to be much, much quicker for us to do, but even the adding and subtracting just has a little bit of our combining like terms business that we might have to worry about doing in the way of simplifying. Like we had done with our regular old functions, we can evaluate. So you see peeking up down here at the bottom, a little bit of g of 0 showing up. What is that really? Oh, it's g over f of 0. Because we're talking about plugging in a specific value for x, we have two options to do that. We can take each individual function and plug in 0 before we do any of the division business. So we can calculate g of 0, we can calculate f of 0, we can then take those two numbers, put the one on the top, put the correct one on the top, put the correct one on the bottom. Or, as a second option, we could just build the generic function g of x over f of x. And once we have that generic function, we can plug in the 0 and run through all the calculation work. And once again, that really basically means we have to accomplish the same things. We have to simplify the numerator, we've got to simplify the denominator, and we're still coming up with exactly that same answer, -5/2. So whichever way you might like better, you do have that option for when you are plugging in a specific value, evaluating your functions. But as it turns out, that's not the end of what we can do. The other main thing that we can do with functions is called composition. And that basically amounts to taking a function and putting it inside of another. So instead of taking an x and putting an x value into your function, you can take a whole entire function and put it in place of the x variable. To put this into a practical sort of sense, I like to use this example here. If you take a keg and put it into a refrigerator, you now have a more complex machine, a machine where the keg part pumps the beer and the fridge part cools things. So together you have this kegerator, and it is a new machine that specifically pumps cold beer. So, nice sort of idea. If you want something that's a little bit less adult-oriented, you could say chainsaw. You've got a machine that spins things around as far as a chain, spins the chain around. You've got a different simple machine, that teeth idea that can cut through things. So if you put the teeth on the chain and the chain is getting spun around by a different machine, you've got the simple machine of the teeth that do cutting, you've got this other machine that is spinning this chain around, and boom, you've got a chainsaw. Similar kind of idea. You're taking two machines, doesn't matter whether they're simple or complex or a mixture, right? It doesn't matter. If you take two things and you put them together, have you in fact created a new machine that can do a new and more complicated, more involved kind of job. Composition in math is that kind of idea. Our functions, each one individually, do their own jobs, but when we put them together through composition, they're doing a new job. We have a different way of notating that we want to make sure that we are aware of. We have this circle symbol that we use, so this open circle symbol that we use, and that's because the way that we kind of phrase this is still using that function language, f of x, g of x by themselves. If we do composition as far as f circle g, that really refers to f of g of x, which means that we want to take the g of x machine and put it into the f function, the f having been on the outside, the g having been on the inside. So f of g of x, the g of x function is getting put inside of our f function. So we can look at an example, say we have capital G of x is 2x minus 7, and capital H of x is this square root of x plus 3. The order that they ask for those compositions has an impact on how things turn out. So when we look at this notation, it's telling us what kind of order there has to be to putting things inside of one another. the capital G is on the outside. So that means that capital H is on the inside. Capital H function is going to get put inside of our capital G function. So capital G of capital H of x. That capital H of x function, I'm going to go ahead and put in the specific version of that. The square root of x plus 3 is getting put into our cap G function. Everywhere we used to see an x, we are now going to put in a square root, specifically square root of x plus 3. So g of x used to say 2x minus 7. Instead of the x, 2, I want a square root of x plus 3, and then there's that minus 7 tagging along at the end. Now let's watch and see what happens when that's a different order. Capital H of capital G of x. Now it's the cap G that's going to be going inside. Cap G is a 2x minus 7. So instead of x, we're going to have 2x minus 7 being put into our capital H function. Capital H has that square root. Instead of the x, we're putting in the 2x minus 7. And the plus 3 still underneath of that square root. Tidy that up, we get the square root of 2x minus 4. These are, got to point at the right stuff. These are very much different looking from one another. They're going to work differently. They're going to look differently when it comes to graphing. So very much important to make sure that we've got the order handled correctly when it comes to the composition stuff. But in math, we have this keen interest not only in doing things, but also asking ourselves, can we undo those things? So when we start talking about, oh hey, there's this thing that we can do called adding, but can we reverse that process? Oh yeah, sure we can, if we do this thing that we'll call subtracting. Hey, we've got this thing called division. Can we reverse that process? Can we undo that? Yeah, we sure can. We can use multiplication. So if now we're talking about, we have this idea of composition, can we undo that? Can we reverse that process? Can we decompose? And the answer is, maybe you're not surprised by this by now, the answer is yes, we can. If we have a function that we are being asked to decompose, we can kind of think of it like peeling an onion. Not very machine-oriented, but just a helpful kind of visual to maybe have, that when we read the function, we want to think of the different things that appear as layers. So what's the outside layer versus the inside layer, to just, again, use that very kind of simple set of descriptions, inside, outside. So what is on the outside? Layer style, onion, right? So inside, outside. We want to keep in mind the basic functions that we've talked about. So we've got our linear function. That's not super helpful for us as far as thinking of like, oh, well, y equals x is a basic function. We're really thinking more along the lines of x squared, absolute value of x, square root, cube root, and now we can also throw in other kinds of radical functions, so any other kinds of roots. We can throw in any kinds of powers beyond just the squared and the cubed. We can throw in rational stuff like 1 over x. So anytime we see some of these basic kinds of things, we want to say, oh, is there a way for us to talk about inside versus outside? Some of these are a little bit more direct than others. So here's this function. Capital, or not capital, regular h of x. H of x is equal to parentheses 2x minus 1, parentheses squared, plus 17. So we could say, okay, cool. Thinking of basic functions, this has the squared showing up. So if my basic idea is an x squared, this has got a lot more going on. What could I say is one version of inside versus outside, if I'm thinking of that idea of x squared? So we could take this idea of inside, because of what we're reading, I have things that are literally inside a set of parentheses. So this is also something that is helpful if we think of inside of a root, inside of absolute value bars, inside of a denominator is also an option, right? So this kind of notion of inside can sometimes be very direct. So inside a set of parentheses. Well, if that's the inside stuff, let's call that inside stuff f of x, just, for convenience, right? F of x is that inside stuff, inside the parentheses, 2x minus 1. F of x is 2x minus 1. The outside, so we've got stuff, well, we already worried about what's inside the parentheses. So we don't have to worry about what's inside the parentheses anymore. We have to worry about what's outside the parentheses, where we have a power of 2 and a plus 17. So the simple way to streamline that, instead of having anything fancy inside the parentheses anymore, we're just going to have a regular old x squared plus 17. So we can have this separate function, g of x, is x squared plus 17. And that would mean that for the composition and the way that we've named things, our function, h of x, is going to be based on g of f of x. So whether we use the function version of things with stuff nestled together, or if we're using that composition style notation with the little circle, g circle f, g of f of x is that way of doing things. We've got to make sure that based on the way that we've named our individual pieces, which is the correct thing? Is it going to be g of f? Is it going to be f of g? We've got to make sure we're paying attention to that sort of thing. But this is only just one way of decomposing things. So just to mention another quick way of looking at stuff, you might say, hey, I think it's really simple to talk about this plus 17 as being on the outside of this squared stuff. So maybe I want to say my version of f of x is going to be x plus 17, a thing plus the 17. And in our case, that thing that is being out in front of the plus 17 would be parentheses 2x minus 1 parentheses squared. So g of x would be the parentheses 2x minus 1 parentheses squared. So there's another way of being able to break things apart based on that notion of inside versus outside, based on that idea of decomposing.